Good morning, or for those remote, good afternoon or good evening. My name is Paul Donahue. I work for Ventana Microsystems, and I'm the vice chair of the RISC-V Debug Task Group. It looks like I'm up against, on the other side, a presentation about 1,000 plus hearts, and that sounds pretty interesting, but it sounds like a debug nightmare from my point of view. So that's why I'm here to talk about debug. And I'm going to talk about RISC-V Debug and the OSA platform specifically. The RISC-V Debug Architecture is a comprehensive set of debug features that allow debugging of anything from the first firmware instruction after reset to just user mode applications and things like that. It supports both external debug, for instance via JTAG, or also native debugs like running GDB on Linux. The best and the worst part of the debug architecture is that basically almost everything's optional. So that allows a lot of flexibility for implementations, that they can support features that easily fit into the microarchitecture or that are necessary for their target market, but you don't have to have all this extra baggage. But the downside is that debugger software doesn't necessarily know what features it's playing with, and there's kind of a seemingly infinite variety of possible configurations. So what do we do about that? Well, the solution is to have a standard subset of debug features defined in a platform standard, and that's what the OSA platform provides. Of course, implementations can go above and beyond this minimum set of features and provide some of the additional features that the architecture allows, but at least there's a common subset that debuggers can work towards. So in this talk, I'm going to go through the architecture and give some of the architecture features, and then at each step, I'm going to talk about what the OSA platform mandates. And one thing I do want to note is the OSA platform is not yet ratified, but the debug feature set has been there for 6 months, has been stable, and there actually haven't been any changes. So I expect it to move through mostly unchanged, if not entirely unchanged. So the architecture requires a way, as I mentioned earlier, to debug from reset. That's certainly important in debugging firmware, but it's optional to support debugging immediately out of reset regardless of the reset cause. The architecture provides a mechanism called reset halt request that provides a standard mechanism for debug after any type of reset, and the OSA platform mandates reset halt request support. The debug architecture is essentially two separate external debug mechanisms. There's abstract commands and there's the program buffer. Architecturally, either one or both could be implemented. Abstract commands can directly from the external debugger access the heart state mentioned here. They have to be able to access the integer registers, but supporting other heart state like floating point registers and CSRs is optional. So obviously, to be able to effectively debug software, we want the debugger to be able to see all of the heart state, not just some subset. But some of you may notice that this list doesn't have everything that all implementations might have. So what about the vector registers? What about custom extensions that have custom register files? How can a debugger access those? Well, not really with abstract commands. So there's this other feature in the architecture called the program buffer. And that can access, it executes instructions, so it can access anything that instructions can access. The program buffer could be as simple as just single instruction injection, like ARM has EDITR, which does that. And there's a mechanism in RISC-V to automatically execute the program buffer whenever a new instruction is written to the buffer, so it's very much like EDITR in ARM. The program buffer, though, is a little bit more powerful because it can allow short instruction sequences to run. So maybe it could read some state out of a custom register file and move it into a temporary register before pushing it out to the debugger, because maybe the custom extension doesn't have a direct path from the custom register file to the debugger. Or maybe it could read memory at some pointer, send what it just read to the debugger, increment the pointer, then you can step through memory and dump out a memory buffer. And the program buffer has the capability to repeatedly execute. So you can, well, it's kind of like ARM's memory access mode, basically, in that example. But one of the really important things is that it's, oh, you know what? I didn't advance the slide, sorry. One of the important things is that, that all legal instructions are supported by the program buffer, as we'll see on the next slide. So that was the architecture. So now we're getting into the platform, what the platform mandates. Based on what I've said, you're probably not surprised to hear that the OSA platform requires the program buffer support. For one thing, that's easier for many implementations. Well, simple implementations can easily access a bank of 32 integer registers. Out-of-order implementations that do register renaming can't just take a register address and directly access it, because they have to go through the rename logic to know which physical register corresponds to which architectural register that the debugger is trying to access. But executing instructions naturally goes through that rename logic. And as I previously mentioned, abstract accesses don't support state other than the three things that I talked about. So anybody who wants vector or custom registers needs to use the program buffer. There's also one additional subtle shortcoming of abstract accesses. Debuggers often write e-break instructions to memory, and this is self-modifying code, so you have to execute a fence.i instruction according to the architecture in order for the instruction fetches to see that e-break that you've injected. And with abstract access, there's no way to do that. One vendor actually created a custom CSR that when you access that CSR using the abstract access to the CSR mechanism, that it caused a fence.i to execute, but that's kind of a hack, and it's just much more straightforward to support the program buffer. And this also allows debuggers to inject S fences and H fences and normal memory fences as necessary. But the OSA requirement, again, does not preclude going above and beyond the program buffer and supporting the abstract access commands. So on accessing memory, the program buffer, when it's executing these instructions, it's in a mode called debug mode, which is essentially like M mode. But there's a couple extra CSRs, and there's some minor differences that I don't need to get into here. But M mode has a feature called MPRV, which is part of the privileged architecture. And that allows M mode to access memory as if it is some other mode that's specified in this MPP field. If MPP is a mode other than M, then it does the page table translations and the PMP lookup as if it's user mode or whatever. And that's very useful. But the earlier versions of the debug spec required debug mode to behave as if MPRV was 0, regardless of the actual value of MPRV. That's convenient if you don't know the state of MPRV when you enter debug mode, and if all of your memory accesses want to be using physical addresses. But when you're debugging software in some mode other than M mode, you want to have a view of memory that matches the thing that you're debugging. So version 1.0 of the debug architecture allows MPRV to be respected if this optional MPRV enable bit is set. Now, the debugger would, of course, need to save and restore MPRV if it changes it. So, whoops, lost my place here. The OSA platform requires MPRV enable to be 1, so that debug mode accesses honor MPRV, and they see memory in the mode of the debugger's choosing. But note that MPRV can still be cleared, and then everything is as it was before. Although the debugger needs to save and restore MPRV if it wants to do memory accesses, it saves a huge amount of emulation effort if the debugger wants to observe memory if it's, say, a user process, especially if it's running inside a guest virtual machine. Because if the H extension is supported, there are 2 stages of memory translation. There's PMP checks. The endianness of user mode can be different than the endianness of machine mode. There's a lot of different things. So emulating a single RV64 load instruction can, by my calculations, involve reading up to 77 CSRs and doing 62 memory accesses. That's obviously a very worst case scenario for misaligned loads and crossing page boundaries and things like that. But just by honoring MPRV, we don't have to worry about any of this. It's just done in hardware. The debugger doesn't have to emulate the whole table walk mechanism. So far, we've been talking about what an external debugger can do once it gets control. But now let's step back and say, how does the external debugger get control to start with? A required feature of the architecture is that it can send an asynchronous signal to a heart and enter debug mode. But that's probably not sufficient, right? And none of what I've talked about so far addresses native debuggers if we want to run GDB on Linux. So the trigger module is the answer to both of those things. The trigger module is the thing that allows control to pass to a debugger, native or external, on certain events. The trigger module provides a powerful set of triggers. There are execute triggers that are like normal PC breakpoints. There's also, you can match particular instruction encodings if you want to stop once you hit a particular add instruction or something like that. There are load store triggers that fire when accessing a particular address or a naturally aligned power of 2 range of addresses. And you can also fire when you see particular data values being loaded or stored. We also have instruction count triggers. This is mostly useful for single stepping if the number of instructions to execute is 1. And there's iTrigger that fires on when you're trapping into an interrupt handler, and you can select which subset of interrupts fire this trigger. And there's eTrigger, which fires on exceptions. And again, you can select which subset of exceptions cause this trigger to fire. So just page faults or just illegal instructions or whatever, or both, whatever. And there are also external triggers that can fire when some other event occurs, such as a performance counter overflow and various things. That is a little bit microarchitecture specific. So all the triggers can either halt or pass control to an external debugger, or they can trap and pass control to a native debugger like GDB on Linux. The load store and PC triggers I mentioned are architecturally allowed to be imprecise. Well, that's not really a super great idea, but the architecture said it's probably better to have some imprecise debug capability than to have no debug capability at all. Triggers support mode-based filtering. So for instance, you can have a trigger fire on when it's executing a particular PC in user mode, but not when executing that same PC in machine mode. Or you can have a trigger fire when you get a page fault in supervisor mode, but not when you get a page fault in user mode. And there's also context-based filtering. So you can match on the address of a load only when there's a particular user process active, but not when some other user process is running. So that's the architecture. So what does OSA say about this? Well, the OSA platform requires the ability to limit triggers to fire in only certain modes, because that's a super useful feature. It also requires the ability to filter on a particular process by filtering either by filtering on being in user mode and either an ACID or the S-context register as an additional filter. And when we take the hypervisor extension into account, it requires the ability to filter on a particular guest. So you can combine these two things and filter on only a specific user process within a specific virtual machine. And once a trigger fires, it requires the ability to pass control either to an external debugger or to the native debugger. When dealing with an OSA-compliant implementation, the debugger can count on these features being present. So at least 4 PC triggers. And I haven't really mentioned it so far, but there are 2 variants of the OSA platform which have mostly the same requirements. Everything I've said so far has been the same. But here's one place where they differ. The base platform spec requires 4 load store address triggers, and the server platform requires 6. Also, you have to support single stepping and interrupt and exception triggers, and it's probably no surprise that triggers have to be precise, because debuggers, you can't, it's very difficult to debug when you have imprecise traps and halts. You may note that there's no requirement for instruction encoding or load store value triggers, but again, implementations can go above and beyond the minimum requirements here. And I think that I would advise debuggers to support these features if an implementation supports them. Cross-triggering. In a multiprocessor system, it can be useful to halt and resume groups of hearts rather than just one at a time. The architecture has a concept of halt groups and resume groups. When one heart in a halt group halts, for instance, due to hitting a trigger, all of them halt as soon as possible. And when one resumes, when one in a resume group, which doesn't have to be the same as the halt group, when one in a resume group resumes, then all of them resume. And OSA requires supporting at least one halt group and one resume group. And finally, there are a few miscellaneous requirements. The debug spec can optionally support disabling interrupts when single-stepping, and OSA requires that because single-stepping into interrupt handlers is generally not what you want to do. And the architecture allows disabling performance counters when in debug mode, and OSA requires supporting that. There's not much sense in doing performance analysis of your debug code when it's injecting individual instructions. The architecture also allows something called relaxed privilege checks. That's not really a good idea. It's not allowed in OSA because the debugger really needs to be able to see memory from the point of view of the thing being debugged, not, and if the debuggee is not able to access memory, the debugger needs to be aware of that. So while this is a pretty thorough overview of OSA, the OSA platform requirements, it only really scratched the surface of all of the other capabilities that the debug architecture has. So read the spec here for much more. And like everything in RISC-V, this is a community effort, so I invite any of you to attend the monthly Debug Task Group meetings. And here's the platform spec, that the portion of the platform spec that deals with debug. And, oh, sorry, there. I've got two computers going here. So, any questions?
All right, yep, give him a round of applause. Let's start there. And we'll remind the people online, please get your questions in. I'll keep my eyes on those. Questions around the room? Yeah, go ahead. I'll repeat it.
Has the group thought about standardizing a way of testing a debug implementation?
The question was, has the group contemplated how to test a debug implementation or a debugger implementation?
There is a suite of tests. It's probably incomplete, but there is a suite of tests in the RISC-V tests GitHub project. But like I said, it's probably incomplete. So yes, there has been thought to that, but it's I'm sure that it could be beefed up. The other thing is, because there's kind of an infinite variety of possibilities, it's really hard to come up with a comprehensive suite. I think by focusing on kind of a subset like this does, that will enable people to come up with a test set that would focus on this platform spec.
Excellent, thank you. Another question behind, go ahead.
How does the debug architecture handle work with atomic operations,
Right. Oh, low reserve and store.
Let me repeat it for the people online. How does the debug architecture handle atomic operations? Load, reserve, store, conditional, blah, 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 blah.
Right. So the AMOs, the AMO instructions, which are single instructions that perform atomic operations, are counted both as a load and as a store. So they would match those triggers. Load, yeah, the LRSC mechanisms, well, you have to be careful when you're debugging LR and SC, and it's probably the best thing for a debugger to do would be to not put a trigger inside the LRSC loop, because it inhibits forward progress, and so I guess the answer is you just have to be careful.
Any more questions around the room? Do you want to say anything about the debug spec and its future and how it's working towards ratification as a final advertisement before we call it good?
Yeah, so the debug spec has been frozen for a year now, and we're making slow progress towards ratification. We weren't, I guess, as top priority as, say, like the privileged spec and some of these other things that have just been ratified. but it's been frozen, and we anticipate having ratification within the first half of 2022. And again, invite everybody to join in and join the party.
All right. Let's give Paul one final hand. Thank you very much, Paul.
Thanks.